Alright, hello. So in this video, we're going to cover charge, current, and potential difference. And this is one of the videos that's going to cover some basic electronics principles. And I know in the last video I said we're going to cover resistance, but I found that better suited for a future video. And just as a disclaimer, it's okay if you don't understand some of the concepts we cover in this video. As long as you have a general understanding or just the gist of what we're talking about, you should be just fine for FRC. Okay. So we're going to start off with what is charge, right? And so you guys probably already know the fundamental charges. You have the electron, which is negatively charged, and a proton, which is positively charged. And if you have an object that has more electrons than protons, it is a negatively charged object. And if you have an object that has more protons than electrons, it's a positively charged object. Okay. You also probably know that like charges repel and opposite charges attract, right? We all know this. And something to consider is that all things have charge. They're, for the most part, they're just neutral, right? For example, I have this wire stripper, right? And the wire stripper is neutral because it has approximately an equal number of electrons as protons, and they're pretty much evenly distributed throughout the entire tool. That's why it's neutral, right? But all things have charge. All things have protons and electrons. Okay. In the law of conservation of charge, it's just like a little tidbit of information, right? The amount of charge in a closed system always remains constant. So for example, if we have a robot, we put our battery in, the amount of charge, or the amount of electrons and protons within that circuit we have running the robot will always remain constant, no matter what. Okay? And finally, we have our a unit for charge, which is a coulomb. I don't think I'm pronouncing that right, but the coulomb. And a coulomb is 6.24 times 10 to the 18 electron charges or proton charges, right? And the way I think of coulombs is just like a giant school bus with a bunch of electrons in it. And you'll see me use the school bus later on in the video. Okay, so coulomb is the unit for charge. Okay. And before we go on to electric current, I want to talk about a little bit about conduction in metals, and this will be useful for a future video when we talk about resistance in wires. Okay, so you can think of this orange box as a piece of copper wire, right? And super zoomed in, right? And we can see the copper wire as like a lattice of copper atoms, right? And in metals, the outer shell of each copper atom, the electrons in the outer shell are not like, they're not stuck to one atom, but they're shared across all the atoms, right? And this creates a sea, what I think is called a free sea, or a sea of electrons. I'm not exactly sure the exact name. You might probably want to look that up. But this sea of electrons, right, is able to freely move around. And when we induce electric field inside the copper wire, the electrons start moving. And it's this movement of electrons or charges that is electricity, right? Something to keep in mind, it's the electrons that are moving, not the protons. The protons remain stuck in that lattice. Okay. Okay, so now we can talk about what electric current is. And so here I have some school buses, which remember represent a coulomb of charge, right? And electric current is the total number of coulombs that pass a single point per second. Okay, so in this case, it'll be the total number of school buses that cross this red line per second. That's how many. That's how many amps. That's the electric current in the wire. So say 5 school buses cross this red point in a second. That means I have 5 units of electric current in my wire, and the units for electric current are amperes, right? And through the equation I have here, the equation is dq dt, which is the calculus version. But for the average current version, it's I equals change in q over change in time, right? Where q is charge and t is time and I is current. And from the equation, you can probably deduce what the broken down units for amperes are, which is coulombs per second. That's what an amp is. Okay, so that's electric current. And generally, coulombs or electric current moves very, very slow in wires. Before the video started, there's a little equation you can use. But just so you know, like before the video started, I did a calculation where I took one of the 12 gauge wires. We'll learn about gauge later on, but one of the wires we use to, say, run an intake motor, the charge in those wires move like at about 0.1 millimeters per second. So charge moves very, very slow in wires. Okay. Oh, that's kind of weird. The point. Sorry about the points. So okay, we've established that we can have moving charges in a wire, but what's the point, right? Like, big whoop, I have moving charges, what am I going to do with it, right? So moving charges are useless without the ability to do work. And we measure this ability for charges to do work as potential difference. So potential difference is work done or energy transfer. That's kind of the meaning of work. When 1 coulomb of charge moves between 2 points. That's potential difference. And the equation for potential difference is dW dQ, or the average version is the change in work or work done over charge, and that's equal to potential difference, which is V. And the units, from the equation, you can kind of tell it will be joules per coulomb, and joules per coulomb is another way to say volts. So volts are joules per coulomb. And kind of to better understand this idea of potential difference, I made like a small diagram. We have a battery here, a light bulb, and 3 points. And so I'm going to ask you, what is the potential difference between, say, the orange point and the blue point? Well, potential difference is the measure of work done, right? And because it's just a wire, and although I'll admit there is some resistance in wire, right? For the most part, the potential difference or the voltage between the orange point and the blue point is 0, or approximately 0. And so if I were to take a multimeter, put it to our voltage setting, and plug it between the orange point and the blue point, I'll measure approximately 0 volts. However, say I do it between the blue point and the red point, and I won't get to how we're able to deduce how the exact voltage that involves something called KVL, which is going to be on the scope of these videos. But if we put a multimeter between the blue point and the red point, because work is being done by the light bulb to kind of take that moving charge and produce light, we can assume it's the voltage of the battery, which, say, the voltage of the battery is 12 volts. So the voltage or the potential difference between the blue and red point is also 12 volts. So for every coulomb of charge, the light bulb uses 12 joules of energy, 12 volts. All right. And so if you're not able to solve these practice problems, don't worry about it, right? As long as you kind of get a gist of what potential difference is and what current is, you should be fine for FRC. But if you just want to try for fun, here it is. So a battery has a terminal voltage of 12 volts and can deliver a charge of 1000 coulombs before it becomes completely discharged. I want you to try to figure out what is the maximum energy the battery can deliver. And the second part is, if the current pulled from the battery is always 1 amp, what is the lifetime in the battery? So I'm going to give you a few seconds to pause. All right. So for part 1, right, we're going to use the equation that potential difference is equal to work over charge. We did that in the last slide, right? And so if we rearrange this equation, well, we can say that work is charge times potential difference. Plug in the values we know. Work is 1000 coulombs times 12 volts. And then finally we get work is 12,000 joules. So the battery will be able to deliver 12,000 joules if fully charged. Okay. And then for part 2, we can use the equation that current is change in charge or change in Q over change in time. If we rearrange the equation, we can get change in time is change in charge over current. Plug in the values we know. Change in time is 1000 coulombs per amp, or for 1 amp, right? And then we can get the final value of 1000 seconds. All right, so that's about it for this video. Please let us know if you have any questions. We'll be happy to answer them. The next video is going to be about resistance and wires. All right, so I'll see you then.